Okay. Good morning, everybody. It's early today, but we continue with these very interesting talks by PhD students. The next one is Michele, Fiori, about Pulsar wind nebulae. Please go ahead.
So, thank you everyone to be here, and good morning. So this is my PhD thesis, and it's called High Sensitivity Studies of Pulsar wind nebulae with the CTA and ASTRI array. So a brief outline of this presentation. So I will introduce the subject, then I will talk about major work that I have done on two Pulsar wind nebulae, young Pulsar wind nebulae, this SNRG 09+01 and MSH 1552, and finally I will talk about the ASTRI CTA data challenge. So the introduction. This work has been done in the field of the very high energy gamma ray astrophysics. But what does we meant when we talk about very high energy gamma rays? We refer to all the photons that have energies that are above almost 100 GeV. So the sources that emit at these energies are called very high energy sources and allow us to study the most violent processes and the most powerful accelerator in the universe. Nowadays, this field is growing fast. In fact, the number of sources that we know nowadays are about 220, and in the future we expect to improve this number greatly thanks to the future instrumentation. One of the most interesting targets at these energies are the Pulsar wind nebulae, since they are one of the most numerous class of identified galactic gamma ray emitters. So, but how can we observe gamma rays from ground? Luckily for us, gamma rays doesn't arrive at the ground, but they interact with the atmosphere. They produce a shower of particles of electron and positron that are highly energetic. So they are moving in the atmosphere at a velocity higher than the speed of light in that medium. And so they produce what is it called the Cherenkov radiation. So at ground we can just use some optical telescope to detect this Cherenkov light and reconstruct the energy and the direction of these incoming photons, gamma ray photons. In the future, there is a major project that has been in process to build. That is the Cherenkov telescope array that will consist in more than 100 of Cherenkov telescopes in the two hemispheres and will have an unprecedented sensitivity and energy coverage. Thanks to the fact that we'll have three types of telescope with the different sizes, going from the large size telescope that will allow to look to the lower energy gamma rays, to the small size telescope that will allow us to observe the highest energy gamma rays. Among these small size telescopes, there is a project led by the Italian astrophysical community, that is the ASTRI mini-array project, that was meant to the production of a prototype for the small size telescope. The prototype is already operative in Serra Nave in Catania and has just produced some very interesting results, such as the detection of the Crab Nebula. And the future improvement of this project is the production of 9 or 12 telescopes, ASTRI telescopes, that will be installed at the Observatorio del Teide at Canary Island. With this telescope, what we can study, Pulsar wind nebulae. What are Pulsar wind nebulae? These are historically defined by their observational property. So they are usually embedded in supernova remnant with a centrally filled morphology. They show a flat radio spectrum and a very broad non-thermal emission spectrum, as we can see here from the Crab Nebula spectrum that goes from the radio to the very high energy gamma rays. Also, they present a very high integrated linear polarization. That means that the magnetic field inside this object are very well organized. So the basic picture is we can see from here. We have the pulsar in the middle of the system. Then we have an underluminous zone. After that, we have a shock and the nebula, that is the pulsar nebula, that is expanding inside the supernova remnant. So what is happening here is that a magnetized relativistic wind of electrons that is powered by the pulsar rotational energy flows freely until reaching a termination shock, where these particles can be reaccelerated, and they can emit via non-thermal radiation, like for example via synchrotron, Bremsstrahlung, and inverse Compton. These sources evolve in time depending on the interaction that they have between, with the surrounding medium, so the supernova remnant or the interstellar medium if they are exit the supernova remnant. So the first phase is the phase where we call it they are young sources, young pulsar nebulae. So we have a nearly linear expansion inside the freely expanding supernova remnant. The second phase starts when the outer radius of the pulsar nebula start to interact with the reverse shock of the supernova remnant. So in this phase, the source starts to reverberate, start to shrink its radius and then re-expand for several times, and this phase can last also thousands of years. Eventually, the pulsar can exit the original pulsar nebula, since there is an intrinsic initial velocity for the pulsar, and so starting forming a new smaller pulsar nebula and leaving behind a relic pulsar nebula. Finally, when the pulsar exits the supernova remnant and start to interact with the wind start to interact with the interstellar medium, form what is called the bow shock pulsar nebula, with a cometary-like shape. Here we can see the evolution of the spectrum, the multi-wavelength spectrum for a young pulsar nebula, where we can see that the synchrotron and the inverse Compton peak decreases in energy, and the synchrotron peak decreases much faster than the inverse Compton peak, since the magnetic field is rapidly decaying in these sources. So in this thesis, what we have done was made perspective studies of pulsar nebulae in the context of CTA and ASTRI array. So we were interested in understanding what can be seen with an instrument like CTA or the ASTRI array. And to do this, we selected two objects that are SH0901 and MSH52, that are two young pulsar nebula. We selected two young pulsar nebula since we can model the multi-wavelength emission, and so made some prediction on what can be seen at higher energy. Now I will start to talk about the real work. So we started studying this source, and we started with simulation, with just some simulation of what will be observed. So we choose it since this is young, is very faint, so is at the limited capabilities for the current instrumentation nowadays, and so is detected as a point-like source, and also detected only at up to 20 TeV. The extension of the source in the radio, we know that is about 2 arc-minute, and so we expect the CTA could resolve it. So we studied it. So we start our simulation, for example, using a radio map of the source, so using as a model. We try to fit it with we try to analyze fitting with different models. What we have found is that if this is the real situation, so the gamma ray emission follow also the radio emission. We could see these sources as extended, and so infer a radius for this source at its energy. Also, what we have found is that we can, so nowadays we cannot exclude any models with a cutoff up to 20 TeV. So, since the current data, the error bar are very high. While if we simulate this source with different cutoff, and we try to fit it and to analyze and fit it with the data of CTA, we see that we can recover the cutoff that we have given in input. These analyses are missing some information, so we are missing the systematic error in this analysis, since the software released just the statistical one. So the first step was to try to add an estimation of these systematics. So to do that, we had to choose some systematics, some sources of systematics. And so we choose 4 types of uncertainties, sources of uncertainties. 2 are related to the knowledge of the instrument, so the knowledge of the effective area, or the knowledge of the knowledge of the energy scale. While other 2 are the related to the knowledge of the background, the real background. So the cosmic ray background and the galactic diffuse emission, since this source is in the direction of the galactic center where the gamma ray emission is very high. So we perturb our data or the instrument response function, and we measure the difference between the nominal values to the perturbed one. And we have done this for hundreds of times, and we measure this behavior. Here we see the percentage error that in function of the energy compared to the statistical error, the behavior of the statistical error. What we have found that is that in the low energy band, the instrumental uncertainties, these 2 are dominant at low energies. While at higher energy, the statistical error starts to increase again, since the decrease of sensitivity of the array. While the background-related uncertainties seems to be low at all energy. This means that with this instrument, we can really disentangle between the source and the background. So the work that we have done after this was asking ourselves, but what we expect? We expect to see a cutoff at 20 TeV, or a cutoff at 100 TeV, or no cutoff. But to do so, we need to implement some models that describe the emission from these sources, the multi-wavelength emission of the sources. And since these sources are sources that are evolving in time, and there is a continuous injection of energy from the pulsar and interaction with the medium around, so there are some energy losses and whatever. So we need some model that describe the evolution during all the lifetime of the emitting particles, So we choose this one zone independent electronic model. That we need to solve this transport equation in order to extract the final electron spectrum, from where we can extract the multi-wave, the photon spectrum. To do so, we need some ingredient. So we need to model the evolution of the radius of the magnetic field, of the shape of the electrons that are injected, of the spectrum of the electrons that are injected in the system continuously, and of course also on the maximum electron energy, and also considering that there can be some escape of particle during time. So first thing was to test our model against observational data and against other modeling, similar modeling that we found in literature. What we have found is that the parameters that we fitted are compatible with the other found in literature. The only thing that we found that we cannot really constrain is that a parameter, that is this epsilon parameter, that is the confinement factor that is linked to the maximal electron energy. We cannot really constrain since this parameter works in an energy band where we don't have any observation. So we just put some lower limit to the maximum electron energy of this source. So after I've seen that our model works, we try to fit our simulation, CTA simulation. What we have found was that the result from the analysis on cutoff on 20 or 30 TeV is compatible to the already available data. But also we found that we can describe with this model or a cutoff up to 100 TeV. What we cannot do it is fit it a model that has no cutoff, so a pure power law up to almost 200 TeV. So finally, for this work, what we have done was to test if, since so the inverse Compton peak in this, we know that is highly dependent on the interstellar radiation field, so the photon background that generate the inverse Compton with the electrons. Was tested if, since when we do our fitting model, we used some diluted black body to describe the emission, the interstellar radiation field. But what if we use a more realistic interstellar radiation field? Does the real shape matters when we are going to fit it? What we have found briefly is that this is not important. We can just use some diluted black bodies, and we can reconstruct the real parameters of the nebula even if we are not using the real shape. So after that we started with a new sources, that is MSH 1552. It's again a young pulsar-wind nebula, but in this case this object has a complex morphology. Shows a complex morphology that is shown in these images here that I will explain now to you. So in red we have these contours that describe the emission in the radio band and describe well the emission from the supernova remnant. In white we have the emission in the X-ray band that describes well the emission from the pulsar-wind nebula itself. Then we have this yellow circle that describes the best fit of an analysis made on the Fermi-LAT data. So where they found that the emission is widely more extended than the pulsar-wind nebula and also a bit misaligned with respect to the center. Then the color map that we see behind is the S data, so in the TeV band, where the authors of this analysis says that the emission can well described by the pulsar-wind nebula, but also there is the needing of a new component, that is this Gaussian component that is external to the pulsar-wind nebula. So what we have done in order to study it for CTA was to study two test cases first. First, we start from the physical modeling on the data that we have, so with the model that I just showed you. So in the first case, we just consider the emission from the pulsar-wind nebula, and considering that all the emission is coming from electrons inside the pulsar-wind nebula. Then we studied a case where the emission are coming from the electron of the pulsar-wind nebula and electrons in this Gaussian component. So in the first case, the modeling, what we have found was that in order to fit the data, we need a real high density for the near-infrared background field that is almost 30 times the expected value from galactic emission models. This discrepancy with the models, the galactic emission models, can be overcome if we consider also this external component. So we are adding a new component, a new electronic population that can emit via inverse Compton. We see that now we don't need anymore this very high energy density for the infrared background field. Also, what we have found was that we can give an explanation to this external component, considering that the total energetic of this electronic population can be explained with just particles that are escaped from the Pulsar Nebula to the interior of the supernova remnant during its lifetime of the source. So, for these cases, we extract these two spectra and we made the simulation for CTA. We found that we can recover analyzing this simulation, we can recover the spectrum that we have given in input. So with CTA, we expect that we can study pretty in detail the two different regions, and so making some trying to understand what is happening in the system. So understanding which is the origin of this external component. Also, what we have found is that if we look at the emission, the centroid of the emission at different energy bands, we see that this seems to shift from southeast to the position of the pulsar, so the center of the Pulsar Nebula. This seems to resemble what we have seen from the first image, where we have this misalignment. So, of course, we will need an instrument like CTA that can study all the energy band that goes from few GeV, tens of GeV, up to hundreds of TeV. So, finally, the last job that I have done was on the ASTRI CTA data challenge. What is the ASTRI CTA data challenge? It's a project that is aimed to the creation of a set of simulated data for the ASTRI mini array. In order to, for example, to test the capabilities of the final array, of course. Also test the analysis chain, and to provide an end-to-end test of the instrument data chain robustness. What we have done was to simulate a realistic three-year observing program starting from an internal call for proposal. So every person in the collaboration proposed some object to observe, and what I have proposed to observe, of course, was the same two objects that I've shown you before. So I was interested firstly in this object, since it's very faint, and probably for ASTRI was too faint, but we would like to see if we will be able to measure a cutoff at energies that are higher than 20 TeV. So for this case, here we have chosen a power law with a cutoff at 30 TeV as a simulation. And what we have found that we can recover the cutoff, but also we have found that also a power law model can describe well this emission. This because, as we can see here, the differential sensitivity of this array of 500 hours observation, we see that we are really at the limiting capabilities. So probably in a different case where a source is not so faint, this measurement can be done in more significant ways. Then for MSH 1552, in this case we were interested in understanding can we disentangle between different but very close sources. So we made we have made a model that is a very easy model, just composing the source with a free radial Gaussian profile, really close one to each other, and we try to analyze and fit it try to see if we can recover the three different spectrum. We have found that the free spectrum can be recovered, but we need to give in input the position. We need to know the position of the three sources. But if we for example, we leave free the position of the three sources, we found that region 1 and 2 are too close to each other, while region 3 can be studied alone. So, so after that, we started to thinking to the future, what we are going to do in the future. So, of course, one interesting stuff was to study which pulsar nebulae, which pulsar nebulae can be observed from the northern hemisphere from Observatorio del Teide with the ASTRI array. So, luckily for us, half of the known TV pulsar nebulae are observable. Also, many sources, many young sources can be observed, like the Crown Nebula, and these interesting sources, that is SJ1813-178, that has debated scenarios for the emission from the sources, from these. So, there are two scenarios that can well describe the emission from this source. One scenario is an hadronic scenario, where the emission can come from the supernova remnant, while the other scenario is an emission coming from this young pulsar nebula, so with a leptonic model. What can be done with the mini array for sure would be to improve the quality of the spectra at energy higher of 10 TeV. As we can see here from the, this is the spectrum from S, and we see here that with 200 hour observation, for sure we can improve this part of the spectrum. Conclusion, so in this work we have studied two young pulsar nebula in the context of CTA, so we have made a perspective studies of pulsar nebula with CTA and ASTRI array. We have studied this object, SNRG 09 and MSH 1552. We have computed a model that describes the emission of this source, and we have found that we can expect a cutoff between 20 and 30 TeV, and that a cutoff, pure power law up to 202 TeV is not expected. For MSH 1552, what we have found is that a two region scenario is preferred for describing this emission, and we have seen that with CTA we can really study these two sources. Finally, with the for the ASTRI array, we have seen that we can barely study very faint sources. Probably it's more interesting to study not so faint sources, or sources that are not embedded in the galactic center emission. While for MSH 1552, we have seen that we can, knowing the position of the emitting region, so starting probably from the observation at other wavelength, we can reconstruct the real shape of the emission. Finally, I want just to mention that other than the work that I'm conducting in the CTA and ASTRI mini array collaboration, I've done during the thesis, my PhD work on the high time resolution astrophysics field with the EQI and EQI Plus project, where I was involved in the observation, in the data analysis, where we have studies, for example, black hole X-ray binaries or millisecond pulsar, and also lunar occultation of stellar stars. So that's all. Thanks for your attention.
Thank you very much. Perfect timing. May I start with the questions? I think you presented investigation on the errors only for young pulsars. Is this applying also to old one? Can you infer that the importance of sensitivity or the statistics of the photons is the same influence for olders?
But of course, I've done only for that sources. Yeah. So probably this depends also on the on the flux of the source. So for other source, we needed to do it, probably we need to do a systematic way to do for other shapes, the spectrum and other fluxes for sources. So I think it's good just for that sources.
So is this something that you intend to do, or somebody has to do it?
No, it is intend to do. I think in the collaboration, someone needs to do it.
Good. Okay. Yeah. All right.
The number of objects that can be observed independent, there are only 21, you say, are this type
of pulsar nebula.
Yeah.
So now we know.
There are many other possible objects.
No doubt that there are many other more possible of objects for example, for the mini array from Osservatorio del Teide. I just studied which pulsar nebula can be studied, since this was the subject of my work. But of course, so we know about 220 TV sources, and I say half of these sources can be observed from Osservatorio del Teide. Then we will probably also unknown sources that we expect to discover.
Can you go to the slide in which you presented the pulsar nebula? There is a picture that has been created. I remember there is a sort of ring which is misplaced with respect to the position of the pulsar.
This?
Yeah.
So, sorry. So this is the let's say the forward shock of the supernova remnant, and this is the reverse shock that is coming inside. This shows this displacement because, of course, the pulsar has a kick velocity that during the time can move from the center of the supernova remnant to the side. This just to show that can be possible.
And about MSH 1552, in test case 1, but it is the same also in test case 2, there are a huge number of free parameters in the model. Some of them doesn't have errors.
Because some, so there are many parameters that are fixed. We need to fix to some expected values. For example, we need to know, we need many parameters. We need parameter that describes the evolution of the pulsar. We need parameter that describes the evolution of the supernova remnant. So we need to know, let's say, made some assumption on the mass of the ejecta and on the energetic of the supernova explosion. We need, of course, these are many parameters, but for sure, like for the one for the pulsar, in this case, are very well known. So we expect that are pretty good. Then the other parameter also, they are inferred from observation at other wavelength. And so we just fitted some of them. We just fitted, like for example, this parameter, this one is the magnetization of the nebula, that is completely unknown one, or the second shape, the second slope of the injection spectrum. This is again mostly unknown, while the first index can be inferred from the let's say the radio observation. So this we have leave free. Also here the near infrared background we needed to leave it free in order to have enough emission to reach this emission in the TV band. So
did you look if how these parameters are correlated?
There are some degeneracy. For example, if we change we can obtain a completely different model, but changing the age of the system. But the age of the system can be, in this case, inferred from the pulsar, from the spin down of pulsar, and is one of the pulsars that is a very well-known pulsar. So we expect that these are pretty.
A couple of slides after, you model the emission with the symmetric Gaussian shape, but if I look at the original image, you have this.
So now, when I have shaped for the simulation, so for the pulsar with nebula, I have used the on X-ray map. So I extracted the emission from X-ray map and I use it as a model. So the emission are following this emission in the TV band. The Gaussian component, of course, is just a Gaussian shape that seems to be not really, but this is just probably also for the visualization. But I choose this shape not by myself, but because there is a publication where they say that the best fit model is a Gaussian shaped for this region, external region. Okay, probably a better model for the simulation can be done, of course, but was not in where we were interested in.
Is it possible to give an estimate of the lifetime of the pulsar?
But let's say for young pulsar with nebulae that.
No, I was thinking of a lot of young or old.
All the pulsar with nebulae.
Well, when you form it, say from the birth of the neutron star, and
let's say
it goes
20 kilo years, 20-30 kilo years.
20 kilo years.
Because after sometimes, so the energetic of the pulsar is not enough to power this winds.
Not to the pulsar going out.
No, because when it goes out from the supernova element, form what is the bow shock pulsar with nebula. So we know many also bow shock pulsar with nebula, but they are all 20-30 kilo year maximum.
And with CTA, how many do you expect, if you work out the statistics of how many you could map in the galaxy so that you could perhaps work out how many pulsars are born?
No, so how many pulsar with nebula we expect to observe is a study that we are doing now. So we are just conducting a population model that we are going to using also this one zone time dependent electronic model to infer the number of sources that we observe. So I think from the first analysis that we are doing, 100 of pulsar with nebula can be observed with CTA.
Also, another curiosity, if I may. The fraction of massive stars born in binary systems is very powerful. So maybe it is possible to have the coexistence of two pulsar with nebula.
Okay. Probably a scenario
and there are many born in binaries and many with a high mass ratio. I mean, equal mass binaries. So maybe it is possible to have.
For sure, we know a pulsar with nebula that is a binary system and a pulsar with nebula.
Okay.
So, yes. But I don't think that is two pulsar. It's just sequel stars.
But Laura, if the duration, is only 20 kilo years, then you really have to be 1.00 in the mass ratio to have them at the same time.
So another question. So about the fitting code that you present, so it's something that you yourself developed, or it was already available and you just run?
No. This is a model that is found in literature, but the implementation has been done by myself. The only thing that I don't have implemented is the software that solved numerically this equation that is this software Gamera. But the dynamical evolution following the literature, I implemented it.
Okay, so another question about the challenge that you participated in the end. So did I understand correctly that you would need 500 hours of observation?
So with astronomy, yes, this object of course, will be not one of the most interesting objects for astronomy array because it's very faint. But yes, for this type of object, we will need at least 100 of hours, 200 hours, 300 hours of observation in order to make to study very well. But also with CTA, the analysis that I presented before, was done with simulating 200 hours of observation. So this is the amount of time that we need.
And do you have any hint about the origin of the Gaussian component, the extra?
No, that, as I said, is probably is from the diffusion of particles that are just escaping, just going outside from the Pulsar Nebula, and that are filling the interior of the supernova remnant. But of course, we need to study with an instrument that has a better resolution to really see these two regions.
Just a curiosity, very short one. Would that be a way to find the neutron star or pulsar in supernova 87A, the LMC, by looking at the pulsar wind and not directly at the pulsar signal? I mean, your objects are all in the galaxy, right?
Yes, all the galaxy. I don't know really the energetic of that system.
Yeah, but in principle, if you observe the pulsar wind, you can find there is a pulsar without the pulsar pointing at you and getting the pulsar signal.
Yes, if we will see the pulsar wind.
Yeah. Okay, good. We're done. Okay, thank you very much.
Because the last few weeks the rumors that the neutron star has been found in the 87A.
Thanks for information.
Sì, esatto, perché c'è sempre una serie. Sì,
Perché non li vedete più alla prossima rivoluzione.
I'm sorry. You passed. Very good. Yeah. Very, very nice work. Yeah. Very impressive, and I think very important for the people building it. Yeah. Okay. Congratulations.
Thank you very much.
Yes. Sorry. Okay, next speaker, next candidate is Luca Foffano about extreme blazars in a multi-messenger context.
Thank you very much. So today we'll be talking about my main activities during my PhD, and the main activities were related to the extreme blazar. So I will be following 4 main points during this presentation. First, I would like to say what extreme blazars are, so mention what blazars are and remind how an active galactic nucleus is composed. Then I will spend some time to talk about my main activities studying and characterizing extreme blazars. So the main question will be how we're facing with a population of extreme blazars, in the sense that extreme blazars probably are not only a new class of sources, but probably there's a population there, so differences among them. Finally, I will be talking about the discovery of a new extreme blazar called PGC-240248 that was discovered thanks to the previous work and to a list of candidates that was proposed to the Cherenkov telescope. Finally, I will mention my contribution to the extreme blazar event during 2017 and 2018. So first, let me introduce what blazars are. You know, blazars are active galactic nuclei, so some galaxies in the universe emit particularly strong activity from their center. For this reason, we call them active galactic nuclei. And you know, because now we have also a picture of that, but at the center there is a supermassive black hole. We have some matter rotating around the black hole, forming an accretion disk. Some other material far at larger distance, and probably also the structure is much bigger, called torus, that is composed by dusty material. Then we have some other material rotating around the rotational axis of the structure and composing the broad and narrow line region. But what I really need to do for this presentation is the definition of this relativistic jet. Because some galaxies show also this structure that are enormous structures. It's difficult to, we don't know for sure how they are composed, but probably the matter rotating around the black hole forms strong magnetic fields, especially collimated around the rotational axis. Part of the circumnuclear matter rotating in the circumnuclear region is probably injected into this jet and is then accelerated, and so we have this enormous structure where actually the matter is accelerated at the highest energies in the universe. So they are among the most powerful, most energetic accelerators, persistent accelerators in the universe. So as you see, the structure is very asymmetric. This is very important because in active reactive nuclei we see different phenomenologies of these objects depending on the point of view. In this case, we will be talking about blazars. So when these active galactic nuclei are pointing their jets directly toward us. This is very important because we can study directly the light emitted by these extreme laboratories. The idea is that if we analyze the spectral energy distribution of these jets, we see that it covers the whole electromagnetic spectrum from radio to gamma rays. It's generally composed by two main humps, the synchrotron hump and what I call high energy hump. I will now mention why. The reason is that when we study these objects, it's well known that the first hump is due to synchrotron radiation. Probably the lightest particles that are injected into the jet, electrons are accelerated and produce synchrotron light. But then it's much more, the second hump is much more debated because in general, most of the blazars is probably interpreted by the synchrotron self-control mode in the sense that probably the photons that are produced, the synchrotron photons produced by the electrons are then reprocessed again by the very same electrons and then scattered at the highest energies via inverse Compton scattering. But, and this is one of the exceptions, in some cases there might be also other processes. So for this reason, it's not only an inverse Compton hump, but it's probably contributed to by more complex processes. There could be other radiation fields that are accelerated, that are scattered at the higher energy, at the highest energies, and also other particles. For example, in the case of extreme blazars, I will now mention, there could be also the acceleration of protons, hadrons. So also these particles produce synchrotron light that is emitted at higher energies. We'll now be back in few minutes to this point. It's very important in this presentation, to remind the definition of blazars, because I will mention why when talking about my main work. The idea is that we define blazars on the basis of its synchrotron peak position. So we don't mind about the high energy hump, we only consider synchrotron hump. We can find actually several subclasses of blazars, and they are related probably by this phenomenological sequence in which we correlate the flux, or better the luminosity, and the synchrotron peak, the energy of the particles that are emitted. And you see that we go at higher and higher energies. So when we talk about extreme blazars, we talk about sources like the violet one. So the most energetic sources of the blazar sequence. Let me now present what extreme blazars are. The idea. So we are talking about blazars that have their synchrotron peak shifted at the highest energies, and in general we use 10 to the 17 Hertz, 0.3 keV. So, and you see that the high energy hump goes at even higher energies. The idea is that the synchrotron hump enters the X-ray band. In particular, in general, it enters the medium to hard X-ray band. And I will mention this in a few minutes. The high energy hump is well detected in gamma rays, and especially in very high energy gamma rays. So when dealing with real data, we deal with spectral energy distribution of like this. 1s 0229 plus 200 is called also archetypal extreme blazar, so it's the source to which we refer when talking about extreme blazars. As you see, there is a small hump here at optical wavelengths where we have the host galaxy radiation, depends on the distance and on the distance of the source. Then we have the synchrotron hump, and then we have on the right the high energy hump. You see that here the high energy hump, we don't see the peak. We see that it's continuously increasing up to about 10 TeV. This is very important. I will be back here in a few minutes. So why do we study extreme blazars? The idea is that they are, for sure, the most energetic blazars, probably the most energetic persistent accelerators in the universe. They extend the blazar family, so they are for sure a new class. They probably extend also the blazar sequence, but there are some caveats about that. I will now mention why I think that actually they are not a class, but they are a population. And finally, an important thing is that we absolutely need multi-wavelength observations to study their emission, because otherwise we cannot characterize their emission. And you will understand why in a few minutes. The idea is that during this thesis I made use of several instruments. In particular, some of them were the Medicina radio telescope in Bologna, SWIFT providing optical UV X-ray data, Fermilat providing surveys of high-energy gamma rays, and finally MAGIC providing the very high-energy gamma rays. Then there are other reasons for which we study extreme blazars, also because their RTV spectrum is very important when interacting with the extragalactic background light and the intergalactic magnetic fields. But the main important thing is that they are very difficult to be modeled. So it's very difficult to understand why we have so strong emission, so strong energy of the particles. The idea is that I mentioned the synchrotron self-compton model is what I was saying before, but the point is that this model works, but it doesn't work so well, in the sense that it provides, in general, extreme parameters, so unusual parameters in the blazar physics. It seems that you are stretching the model, so something is not working properly in some sources. And for this reason, we use much more complex models on some sources. For example, we use multiple emission zones. For example, the jet, we think that it could be composed also of two regions. For example, a fast spine at the center and a slower sheet around it. Or we consider also more complex reactions, like the presence of hadrons in the jet, or the interaction between hadrons and leptons. In this case, you see that extreme blazars might also be the neutrino producers. So this is another reason for which extreme blazars might be also producers of neutrino, and they enter this multi-messenger context. I would like now to present my main activities concerning these extreme blazars. So what's the problem? Why I'm talking about the population? I've shown this SED a few minutes ago. This one ES0229, but I can show you also this other SED. This is Markarian 501. I can now compare them. You see that they are quite similar except for two main points. The flux is normalized. The synchrotron peak position, but the difference is quite modest, around 1 order of magnitude. It's not particularly interesting on my point of view, but the crucial difference is in gamma rays. Because there you see that while 0229 in black is its spectrum is continuously increasing up to the TV regime, Markarian 501 is not, and it's peaking at a few hundred GeV, so 2 order of magnitude at least before the 1ES0229. And it's very different. So is this a casual difference between two sources, or is this a more complex, systematic difference in the blazar class? So this is what we did in this first publication about extreme blazar. The idea is that we need to find a larger sample of sources, compare them, and understand if there are the same difference or not. So the idea is that we selected extreme blazars on the basis of a hard X-ray of a new catalog in hard X-rays called Swift Path under 5 months. And the selection in hard X-rays allows me to select almost all extreme blazars because they are peaking there. So their luminosity there is quite strong. So it's quite straightforward to select their extreme blazars. I selected 32 extreme blazars. This is up to date, probably the largest sample of extreme blazars, and that have been corrected, and we took care of misclassification errors. So But then we built the SEDs, and the result is that these 32 objects, among which we find both known and unknown sources. This is very important because sources that are already extreme blazars are there. This sample is subdivided, split in two main parts, TV gamma ray detected sources and TV gamma ray undetected sources. So sources for which we have the full information through the electromagnetic spectrum, some others for which we don't know where the high energy peak is peaking. So the point is that we now present the first case and then the second one. So the idea is that we can we can look for the same differences of the two sources before in a much larger sample. And this is what we find. Because you see that there is a spread in the flux over more than 2 orders of magnitude in gamma rays. But then, if we focus there, you see that the spectral shape is different. You see that we can see two different behaviors. This is a sketch for sure, but the idea is that some sources are continuously going up in gamma rays. Some others are clearly peaking before the gamma ray, before the high energy, very high energy gamma ray, so above more or less 100, 200 GeV. And this is a crucial difference. And if you see here, we can actually split, we can characterize these two different groups. So if we fit the last part of the gamma ray spectrum, we can actually understand, we can split these two groups. So for example, in the case of 0229, it goes continuously up, and the other one is peaking before, so the slope is decreasing. If we do that for the whole sample, we find that actually we have this plot, so the gamma ray slope spread over the synchrotron peak. But the idea is that we find two main groups, two main clusters, from my point of view, that we now mention why. The idea is that on the right we have sources like 1ES0229, so those continuously increasing up to 10 TeV. On the left-hand side, we have sources that are clearly curved and they are peaking a few hundred GeV. So I will call the former RTV blazars, the latter HBL-like sources. I will now mention why. The idea is that in the middle, I see a source H2356. That actually you see that the error bars are larger, but it's meaningful in my opinion because it means that it's peaking, since I'm fitting between 100 GeV and 10 TeV, it means that it's peaking at 1, 2 TeV, something intermediate. It's an intermediate property between the two classes. So the point is that the two opposite classes are very different. On the right-hand side, the RTV blazars are known to be to show no flares, so no flux variability. They have this RTV spectrum, it's very well known in this community, because they peak above probably 10 TeV, we don't know where. But on the other side, we have sources that are peaking well before the TeV band. They show flare, they do show flares, and they have general high flux variability. So completely different behaviors. And another point is that HBL-like extreme blazars, I call them HBL-like because they are very similar to the previous class of blazars that in general is very well reproduced, interpreted by the standard models. The RTV blazars, on the other side, are completely, in general, very difficult to be interpreted on the light of the standard model. So, in my point of view, we are comparing standard, let's say, standard blazars with non-standard blazars. In the middle, there is this transitional class. I call it transition, in the sense that my question is there a continuous transition between these two classes? Because the idea is that if there is a transition, I'm going from standard to non-standard sources. So I'm not only talking about, sources, I'm talking about physics, because here there is different model, different physical emission probably behind these differences. I will be back here in a few minutes. Now let me introduce the second part of this work, So what can we do when the gamma ray information is missing at TV? We don't know where the high energy peak is. So we can prepare a list of sources. We check their detectability by the Cherenkov telescopes. We extrapolate basically the high energy spectrum to the very high energies, taking into account the spectral shape, taking into account some absorption effect due to the EBL. We compare the sensitivities with of the current Cherenkov facilities and also CTA. So the point is that we actually can also provide this list to the Cherenkov facilities, and we actually, in few months, we had the opportunity also to detect the best candidates. It was a very nice success because this is PGC 240248 that was mentioned before. It was a very nice success because actually they are very difficult to be detected in TV. Very, very difficult, because in general the luminosity there is not good and they suffer of strong absorption effect due to EBL. So it's very difficult to understand how the spectral shape is at TV and then to propose it to the current Cherenkov facilities that whose sensitivity is not yet perfect for this kind of odds. But it was very, very nice opportunity. And this is the multi-wavelength SED. We had the opportunity also to compare it, to apply different models. But the most important result, from my point of view, is that if I bring this source to the previous plot, actually I found a new transitional extreme blazar. So one of these sources that is located exactly in the center of the plot where I wanted to check if, to see if there is some more sources, some more statistics there. So the point is that probably, in my point of view, this is suggesting that there is a continuous transition between let's say standard and non-standard blazar, HBL like the RTV blazars, and probably we can now find out a lot of these sources. Finally, a few words about this neutrino blazar event, because you know probably that on September 2017 we have the opportunity to detect this neutrino coming from a flaring blazar. So I had the opportunity to be main analyzer for the MAGIC data. I was on the front line of this event. As you know, there was this alert by IceCube detecting an extremely high energy neutrino on September 22nd, 2017. After a few days, there was also the detection of gamma rays coming from a blazar located in spatial coincidence with the neutrino, the direction of the incoming neutrino. And these gamma rays were produced by a blazar that was flaring. So it was exactly in that moment in high state activity. It was a very nice opportunity. Then thanks also to the redshift estimation by Simona Paiano et al. 2018, we had the opportunity to take a look at the intrinsic emission of these objects. And the spectral information supports the neutrino, the neutrino blazar coincidence. And this is probably the first, how they called it, multi-wavelength and multi-messenger SED. For sure, then we had the opportunity in MAGIC to follow again this source for several days. Now it's under monitoring for sure, but the point is that after more or less 1 month, we had the opportunity to detect the lower state, another flare, and we had the opportunity to compare it with the previous flare, and these results were extremely useful to interpret this information on a multi-messenger platform. For sure, this was the first the first event in which we had the coincidence between an extragalactic source and a neutrino of the blazar kind. But I think that there are many questions to be answered about this event. So few words about the conclusion. So except for this contribution to the neutrino blazar coincidence in 2017, I had the opportunity to study extreme blazars, this category of extremely energetic sources. I characterized these sources. I had the opportunity to propose a new method to select them. It's very difficult to select them. We prepared the sample of 32 objects, finding hints of subclassification in this class. So probably there is a population there. And the discovery of PGC 242248, I had the opportunity to propose to MAGIC and then to observe and to detect. In my opinion, it suggests, it confirms, it supports at least the existence of a population of extreme blazars. So the question now is, why are we facing with a population of extreme blazars? So what's going on there? So what are the differences in these sources? Because actually the models are suggest that there's something is going on there. So probably there's some complex emission that is not exactly the standard emission. I think that this is the right moment to do that, because now we have discovered a lot of, a lot, 10, 20 sources of this kind, so we can now compare them, we can now study these on the basis of richer statistics. So I think this is a very good opportunity to do that. Thank you.
Thank you very much. That's really fascinating. My first question would be, I didn't get that, your prediction or your selection of candidates, yeah? On what grounds have you proposed these objects?
So the idea is that
based on the low energy pump?
On the high energy gamma ray spectrum, because the point is that we have the opportunity to we have a monitoring of this source in the high energy band, because we have the Fermilab telescope. So for sure this is an average spectrum, but it tells us how it's going, how it's behaving there. And since in general in these sources we show no flux variability, we trust this spectrum, and then we apply extrapolation by assuming some spectral shape. And then we compare it with the...
Okay, so you have some information about the high energy peak, and in connection with the flaring properties, then you say this is a likely candidate. Is that
yes, but actually we don't expect these sources that flare.
Yeah, exactly.
That are flaring,
yeah, because it's absent, yeah.
It happens on some sources. This is the most interesting point, that in some sources they flare, some others are not. But probably we have enough information to see how it behaves at very high energies.
Okay, good.
I have two questions. One you already answered. Is there a transition in between the two classes? Yes. And the other one is still open. Do you have a need about the differences, the extreme difference between the two classes? Why you have this? You said it is the moment in order to investigate this, but any suggestion?
My answer is no. It says that it's very difficult to understand what's going on there. Probably the simple thing is that when we apply more complex models, we are applying more complex processes. So probably there is not only the main leptonic processes, so the standard synchrotron self-quantum model, but we have the contribution also of other processes. So for example, leptodronic models. So this is probably the main reason for which we are, because probably the relativistic jets are so energetic that can accelerate also hadrons in such a way to produce differences on the emission we detect. So probably this is the reason for which we see this difference. But I think this is what we have to assess in a more systematic way, because there are a lot of models that can be applied. But I think that the key is that we actually see a difference. In the very same class, we see difference between HBL-like and RTV. And so probably it's there where we can play. The detection of PGC 242248, it was particularly interesting because you can apply several models, all of them work, but the parameters they provide you, suggest that probably something is happening there. For example, when you apply proton synchrotron models, is only so when you consider that only protons are accelerated beside the electrons and they produce synchrotron radiation, you see that actually it's very difficult to detect, to interpret the highest part of the spectrum. So probably yes, there are also protons, but it's not enough. Probably we could think also the 1D conical jet model that is a time-dependent model, but is always based on the standard model. But it's, yes, it works, but it gives results far from the equipartition that in general is expected in this object. The best model is the spine-layer model, that is the one I was mentioning, so where we have a jet that is composed of different parts, a fast spine and a sheet around it that is lower. This relative motion enhances the reactions and makes these sources easier to be interpreted. So it's difficult, but probably we are.
So the takeaway message is it could be the energetic of the jet.
Sure. Probably the energy, the energy of the particle that is reachable there makes the difference.
Connected to this, would it be a difference in the engine or in the configuration of the surrounding?
It's a difficult question, but thank you. It's very nice because actually when we compare blazars and the different subclasses are probably related to different environments. So the structure of the jet itself or probably around the jet. So in general, the main idea is that the environment around the jet is, in this case, poorer. So the particles can get accelerated to the highest energies without cooling, so interaction with the environment.
Do you have absorption? Is it possible to absorb this very high energy photons?
Yes, it depends where. Because, for example, in the case of the neutrino blazar, but it's not an extreme blazar, but this is the idea, a very important information coming from the very high energy gamma ray spectrum is that we actually have, this is the observed spectrum, but also when the absorbed, so when you take a look at the intrinsic spectrum, you see a bending at very high energies. This bending is probably related to the absorption of gamma rays internal to the jet. So yes, except for that we have also absorption outside the jet due to the distance, so due to the interaction that then these gamma rays have with the, for example, the extragalactic background light.
I would like to know if it exists some other difference in the spectrum of these two classes of
in my opinion, at the moment I didn't find any other, because the problem is that yes, you can find some differences, but on individual sources. When you study them on a sample like this one, it's much more difficult. You can take a look at the luminosity, you can take a look at for example, but I mean it's very difficult because, for example, it's very difficult to fit the spectrum. This is not I mean, this is only an example, but the idea is that it's also very difficult to get this information. In this work, it was very difficult to, let's say, fit the synchrotron peak, because there you have X-ray data, probably the tail of the emission of the electrons. So probably, so there we have strong flux variability. Also, if in general it's very modest, very so. But the point is that it's very difficult also to detect this information about these sources. So it's very difficult to say if we have other differences. At the moment, I don't think so, because in general, this is an interesting point about this work. The point is that in the community, I think there is some confusion about extreme blazars, because when you talk to people think that in general extreme blazars are only of the 0229 kind, so this RTV spectrum that goes to 10 TeV. But this is not the case. The idea of this work was to come back to the definition of the extreme blazars, and then we see what happens at gamma rays. And this is what happened after this, let's say, put in order the information we have about extreme blazars. Because the point is that at the beginning we discovered the 0229, it was the first to be discovered. But then people didn't know how to handle these different sources of the HBL-like sources, because they are very different, because they flare. It's something that is not expected in the extreme blazar class. But I think that actually it's, yes, they are extreme blazar, but they are different types of extreme blazar. we have to work on this, but it's so I'm not sure there are other properties, unfortunately.
So can you go back to your diagnostic plot where you classify
this one?
Yes. So the x-axis here.
The fit of the TV spectrum. So the fit of the.
It's the position of the peak, or.
No. It's the slope. It's the slope. The gamma ray slope. This is very important because
the slope before the peak or after the peak.
That's the point. It's said that it depends on the sources. When talking with about RTV blazar, the peak is after for sure this part. In the case of HBL-like sources, since they are peaking in the 100 GeV, the peak is slightly before. But this is the point, I mean, because I need to understand where the peak is. So here I know that the slope is positive, so the peak is after this value. In this other case, the slope is negative, and I know that the peak is before this region.
In order to put this object in this plot, you needed the magic data, right?
Sure.
So is it available for all the others or not?
In this case, yes, archival data. But this is not true for the other part of the sample, the TV gamma ray undetected sources. And for this reason, we provide a list of candidates. But it's very difficult to have TV information for these sources, because I was mentioning the point is that their luminosity is not good for Cherenkov telescopes, and the point is that it's like looking into the dark. You don't know if that source you will detect it or not. So, and because in general you do observations on the basis of 50 hours observation, so something that for Cherenkov telescope is reasonable. In some other cases, for example, in the case of 1 ES229, you need many more hours to be detected. So in the framework of we need to detect new sources, but in a reasonable amount of time, PGC was one of the criteria. For probably I forgot to mention that one of the criteria the criteria to study these sources and to propose them also to a Cherenkov telescope was the expected integration time to detect them. In the case of PGC, it worked.
Okay. Okay, then thanks again.
Thank you.
Speriamo. Conviene che la copia. Sì, c'è una questa immagine. Ok.
Se vuoi te lo posso partire io.
Ah, ok, perfetto. Pensavo di usare questo, che se riesce a vedere quanto tempo ha. Aspetta,
disponibilità. Ok.
Buongiorno. Io sono Mauro di Demography.
Sì.
Come sta andando? Sì, lo rivedrò dopo.
In realtà dovrebbe essere all'osservatorio perché qui oggi stiamo facendo i dottorati. E ha sbagliato l'edificio, però se vuole.
Perché ieri era
qua? Sì, ieri era qua, però oggi. Se vuoi te lo faccio partire io da qua.
E la faccio proprio per vedere se funziona il. Perfetto. l'altro è banale. L'altro puoi solo mandare avanti.
Vabbè, ma tanto...
Mi sa che ce l'hanno un attimo.
Very well. Okay, congratulations. Of course, you passed, and
Thank
the
you.
committee graded your thesis as extremely good. Yeah?
Thank you very much. Thank you.
Nicola? Good. The next speaker is Nicola Giacobbo, sorry. Demography of compact object binaries in the area of multi-messenger astronomy. You have it again. Yeah?
Thank you. Good morning, everybody. I'm Nicola Giacobbo, and today I'm going to talk about the work I have done during my PhD under the supervision of Michele and Mario Spera. The title is Demography of Compact Object Binaries in the Era of Multi-Messenger Astronomy. So, here is the outline of my presentation. I will give you a brief introduction of the topic, then I will describe which is the aim of my study, and after that I describe my results, and finally I will summarize my conclusions. So, about 4 years ago, the LIGO interferometers have detected for the very first time a gravitational wave signal originated during the merger between two black holes. And this event has revolutionized our knowledge, and it marks the dawn of gravitational wave astronomy. Here, in this cartoon, I show you on the left the masses of both black holes and neutron stars in different color according to the way they have been measured. And in particular, the red big dots represent the masses of black holes inferred from gravitational wave detections. You see that black holes can be more massive than 30 solar masses. Gravitational waves tell us that double black hole binaries exist, and so far that both black hole binaries and neutron star binaries can merge in less than a Hubble time, emitting gravitational waves. So, we observed those objects, but how we can form compact object binaries that can merge in less than a Hubble time? During my PhD, I tried to answer these questions. We know that black hole and neutron star are the final stages of massive stars, so understand the single stellar evolution is crucial to understand the formation of compact object binaries. And there are some critical ingredients like stellar wind and supernova explosions that tell us how the progenitor star is linked with the mass of the compact objects. Since LIGO and Virgo have detected binaries, we are talking about binaries. So here I show you in the middle a possible path, evolution path of a massive binary, of a massive star binaries that can form a compact object binaries that can merge. You see that there are many processes involved, because when we are two stars in a binary system, those stars can interact each other, and many of those processes are still uncertain, but they are crucial to understand whether the binary survive and form compact object binaries. A powerful tool to study the evolution and formation of compact object binaries is represented by the population synthesis. In particular, we use during my PhD these tools, and here there is an overview of the main topic I have covered during my research with the main results. Since I don't have enough time to go into details for all of them, I decide to focus on what was my main task, which is the formation of merging compact objects from isolated binaries. To do that, the first thing I did is develop MOPSI, which stands for Massive Objects in Binary Stellar Evolution. MOPSI is a population synthesis code, a customized version of the widely used BSC population synthesis code. In this cartoon, I summarize the main upgrades I have introduced in MOPSE. In particular, I include in MOPSE new recent stellar winds description, new mechanism for the supernova explosions. MOPSE accounts for the pulsation and peri-instability supernova and peri-stability supernova, and I have introduced a new prescription for the treatment of the natal kids. So here I show you the mass of the remnant as a function of the initial mass of the progenitor stars for different metallicity. And it's evident that there is a strong correlation between the mass, the maximum mass, and the metallicity. In particular, the lower the metallicity is, the higher the maximum mass of the heaviest black hole. The reason of that is that stellar winds depends on metallicity. But there is also another important ingredient, because I introduced in MOPSE the dependence on the Eddington factor for the stellar winds. Because theoretical models show that when a star approaches the Eddington limit, namely gamma close to 1, its mass loss becomes almost insensitive to the metallicity. And it has a strong impact on the shape of the mass spectrum. Here I show you the case of standard MOPSE, where I include the dependence of gamma, the solid lines, and the case where I don't use the dependence of gamma. And you see that there is a very strong difference. So I used MOPSE to evolve large grids of massive binaries, and here I show you the total mass distributions of all black hole binaries formed in a simulation of about 200 million binaries for different metallicity, the different colors. And here on the bottom, the total mass of the subsample of black holes binaries that merge in less than a Hubble time. You see that only at low metallicity we form the most massive system, and that the decrease in the metallicity increases the number of mergers. But it is worth to notice that the most massive system do not merge in less than a Hubble time. The reason of that is that such system, the progenitor stars of such system, develop very large radii during their evolution. So if the initial separation is relatively small, the star merge before become black holes, or they go through a strong mass transfer that lead to the formation of lighter black hole binaries. On the other hand, if the initial separation is large, the stars do not interact, so the outcome will be so large black hole binaries that cannot merge in less than a Hubble time. I define a way to measure how efficient is the production of mergers in a population, and so I defined the merge efficiency eta as the number of mergers per unisolar mass over a Hubble time. I do an example. If we have a population of about 10,000 solar masses that produce 10 mergers in a Hubble time, the merge efficiency will be 10 to the minus 3 per solar mass, per unit solar mass. Here on the right, I show you the merge efficiency as a function of the metallicity for all the three kind of compact object binaries: black hole binaries, neutron star black hole, and neutron star. You see that there is a strong dependence, the eta that strongly depends on the metallicity for both black hole binaries and neutron star binaries. While for neutron star binary, the dependence on the metallicity is weaker. When we study the evolution of binary system, an important phase is represented by the so-called common envelope. And here I reported a schematic representation of the case when we have a compact object, a black hole or a neutron star, in binary with a evolved star. When, if the star overfills its rush lobe, the star starts transfer mass to the companion, which is a compact object, and if this mass transfer is dynamically unstable, the material starts accreting around the compact objects until engulfing the entire system. At this point, both the compact object and the core of the star start to spiral in, and during the spiral in, they transfer orbital energy to the envelope. And if such energy is enough to eject the envelope, the outcome will be a tighter binaries that might form a merging compact object binaries. On the other hand, if such energy is not sufficient to eject the envelope, the result will be a black hole or neutron stars surrounded by the envelope. In population synthesis code, the standard way to determine the outcome of a common envelope is to use the energy formalism, where we compare the difference in orbital energy before and after the phase with the energy of with the binary energy, the energy needed to eject the envelope to infinity. And here in particular, I show you the alpha lambda formalism, where alpha and lambda are two free parameters. Alpha describes the efficiency of transferring orbital energy, and lambda describes the binding energy of the envelope. To understand and study the impact of the common envelope on the formation of merging compact object binaries, I decided to consider three different values of alpha, actually 1, 3, and 5, so different efficiency in ejecting the envelope. And here I show you the merge efficiency as a function of the metallicity for all the three kinds of compact object binaries. You see that the merge efficiency is boosted if we consider that the envelope is easier ejected during the common envelope, while for both the neutron star black hole and black hole binaries, we notice the opposite trend for higher metallicity, while at low metallicity the trend is more complicated. Another crucial phenomenon that we have to consider when we study the evolution of a binary system is represented by the natal kick. When a supernova explodes, because of the material is not perfectly symmetrically ejected, the newborn remnant receive, as schematized here, receive a kick. And so a massive binary that must to survive the kick if, in order to become a compact object binaries. In the literature, there are many studies that try to model the natal velocity distribution of both neutron star and black holes. For black holes, the problem is that we don't have a lot of data, so we cannot reconstruct a distribution. And here reported a recent study of ASTRI and al., where they study they try to infer the potential initial velocity of 17 black holes from X-ray binaries. On the other hand, for neutron stars, we have much more data, but things are still uncertain. For example, some author like Hobbes suggests that a Maxwellian distribution that prefer high velocity well represent the natal velocity of neutron stars. But there is an increased number of studies that claim that not all the neutron stars are born with strong kicks. And in particular, Verbund and collaborators propose a bimodal distribution for better represent the natal kick velocity. But what we do in population synthesis? The standard approach is to draw the natal velocity from a Maxwellian distribution. And the most used is the one proposed by Hobbes. But in the recent years, people start using different Maxwellian for different supernova explosion mechanisms. For example, we suppose that electron capture supernova are less energetic and they eject less material, so the kick will be weaker, and so we use a Maxwellian for low kicks. On the contrary, in contrast, for core collapse supernova, we use high kicks velocity. For black holes, we draw the natal velocity from the same Maxwellian distribution, but we rescale the velocity for the fallback, the material that fall back on the remnant. So I propose a new universal approach, which is still a toy model, but at the advantage to be universal and to include basic physics. So I consider that the strength of the kick is related to the mass ejected during the supernova explosions, and this is supported by hydrodynamical studies. And moreover, I consider that the velocity, the natal velocity, is proportional to the inverse of the mass of the remnant because of the conservation of the linear momentum. So now I will show you the results for 3 different models. 2 where I use the standard approach. In particular, I consider in one high Maxwellian distribution, the Maxwellian proposed by Hobbes, and in another one distribution usually used for electron capture supernova, so low kick. And the last one where I use my new approach. So here you see the natal velocity distribution for all 3 set of simulations that I obtain evolving single stars. You see that with in the standard approach, I have 2 peaks, one in each simulation, while in my new approach, we have 2 peaks, one at low velocity, which is due to the electron capture supernova, and the other one, which is the standard peak for core collapse supernova. But here we are only considering single star. In binary, we have this. Here I show you the same distribution, but for neutron star that explode in binaries. And you see that for the standard case, for the standard approach, the distribution don't change a lot. They show the same peak in the same position, while with my new approach, we still have the same 2 peaks in the same position, but you see, we have also this bump between the peaks, and this is important because this captures what happened in binaries. I mean, a star that undergo a core collapse supernova in binaries might lose a lot of material because the companion strip it during its evolution. So when the explosion occurs, the mass that can be ejected is less, so the resulting kick will be weaker, and so we tend to have a lower natal kick velocity. And now I show you also a subsample of the neutron stars that are still bound after the supernova explosions. you see that there is that to remain bound, lower kick are preferred. Because as I said before, if a kick is too strong, can easily destroy a binary system. So, I think that the LIGO-Virgo collaboration can infer from gravitational wave detection is the local merger rate density. So I try to estimate the local merger rate density starting from my results, actually the merge efficiency eta. I developed a data-driven approach where I coupled the merge efficiency eta with the cosmological metallicity evolution and the star formation as a function of redshift. Here I show you 3 panels, one for each type of compact object binaries, and the shaded areas represent the 90% credible interval inferred by the LIGO-Virgo collaboration. The different marks indicate a different assumption for the different model for the evolution, cosmological metallicity evolution. Here you see that for both black hole binaries and neutron star black hole binaries, I can match the local merger rate inferred by the LIGO-Virgo collaboration in all cases, while if we see the thing for double black hole binaries, we see that if I consider high kicks, I cannot match the local merger rate. But if I consider the low kicks, I can, but low kicks do not match the velocity distribution of Pulsar. And instead, with my model, where with my new approach, I can both match the distribution of natal kick velocity and the local merger rate. So, this is more or less the main results I have obtained during my during my PhD. So, to summarize them, I found that the heaviest black hole can form only at low metallicity because of the effect of stellar winds. That the most massive black hole binary do not merge in less than Hubble time, at least from isolated binaries, but things are different if we consider dense environment. Then I show you that the merge efficiency for both neutron star black hole and black hole binaries depends on metallicity. In particular, we have a higher efficiency, merge efficiency at lower metallicity. We see a different dependence on the common envelope efficiency for black hole and neutron stars. And finally, I have shown you that low kicks are crucial to form double neutron star binaries, and are crucial, especially for those systems that will merge in less than a Hubble time. So that's it. Okay, thank you.
Thank you very much. First question.
I think I would have maybe concentrate only on the alpha parameter.
Yeah.
You get alpha equals 5, correct?
Yes.
Which means that you are over efficient in shrinking the system. So, I mean, alpha equal 1 should be the maximum alpha allowed by that mechanism. If you introduce so you create alpha and you have it to have as big as 5. Do you have any idea how this can be realized?
Yeah, the reason can be that we underestimate some source of energy. What kind of source? For example, the ionization. So the ionization energy that we can have during the common angle phase, or may have the nuclear energy source in the disk, or for example enthalpy. So yeah, for the standard approach, alpha is not physical, but what we want to say with using alpha greater than 1 is that we can only match the observation of the LIGO-RIGO collaboration, only assuming such high value.
And this, I'm not sure I understood correctly. So if you have a too low alpha, you merge prematurely your systems or what? Why are you not able to?
Yeah, that's true for the.
You do not get in the right range of the final separation.
Yeah, exactly. This is true for the neutron star. It's different for black holes because the radii.
But for black holes, you don't have observations.
Yeah, of course.
So it doesn't matter. That's completely speculative.
Yeah.
Okay, Laura.
Do you have some comparison with the observation data that can support some of these simulations? I have not seen any comparison with observational data.
But which part of the simulation?
Most of them simulation.
And then same question too. Exactly what's thinking the same.
Okay.
For example, for the natal kicks. Maybe
Okay, for the
most important part of the.
Yeah. Okay. So for the natal kicks, we.
Yes, just to complete, sorry. You have different prediction, then you introduce your own prediction, and how do you think to validate which is the right one or the more reasonable among these, let's say, 1, 2, 3 possibilities?
Yeah. So far, sorry. The study with a larger sample is the study done by OPS.
So these are the observations?
Those are observations, yes, sorry. Those are observations, yes. For example, the OPS used about of 200 Pulsar, but only 73 to determine this distribution, and most of them on single pulsar. So we, with OPS, we lose the evolution of binaries pulsar. Instead, other studies like study about galactic double neutron star or X-ray binaries show that some neutron stars have to be low kick when they burn, because otherwise the system, we don't have the system. The kick is so strong to disrupt the system. So yeah, I can, so the point with my new model is that I can use a single prescription that include different distribution due to different supernova mechanism, just assuming that the kicks is related to the mass ejected. So I don't have to impose any particular low kicks or high kicks for specific ad hoc.
And then you go back and compare with that.
Yes, for single distribution. For single neutron stars, I match the OPS, which is the red line. That's why I choose OPS in one of the 3 models, because maybe I didn't say that, but I match with my model the single distribution observed by OPS. In binaries, of course, I don't have many data to to compare with.
I always have a question.
Yeah.
I mean, you're talking here only about the kick velocity, but actually the hydro models tell you that the kick direction could be any. So what are you assuming in that respect?
Yeah, I use
isotropic.
Okay. Yeah.
Which is, so to first order, I would say the appropriate approximation. But of course, then in second order, you can think, well, but if you have a tidally non-spherical object, then of course you may have a preferred direction. Of course, that's the next thing.
There is also, of course, this is a toy model, because also the asymmetries can be more complicated than the mean value for the ejector.
Exactly,
so, the model is just a toy model. The real thing is more complicated. Yeah. But in population synthesis, we need something fast. So,
And what do you assume for the connection between initial, say, zero age main sequence mass of the objects and final object type, neutron star or black hole? Because this is now an ongoing area of research. In what mass windows you get a black hole or a black hole after fallback and so on? What do you assume for that?
Okay, I use the Fryer description for the supernova explosions.
Okay.
So in particular, I consider both the delayed model and the rapid model.
Yeah. Okay. This is of course one of the underlying uncertainties as the Hurley relations for cell evolution. You can put in whatever you want.
We also use, not in MOPS so far, but in other different population synthesis code 7, also the compactness.
Yeah,
principle
right. Okay,
of compactness to estimate.
That's the standard way now.
Yeah.
Okay. You had.
I had a similar question about the kick. So, for example, what is the kick in the case of binary? So it's the kick that each of the two components receive. So.
Do you mean in my? No, sorry.
Yeah. So how the kick enters in the case of binary? So each of them receive an independent kick.
Yeah, exactly.
Random.
Yeah.
So they can get.
Yes, because in population synthesis we estimate the kick from the stellar evolution. Then we check if the kick is strong enough, the direction to destroy the binary or not. But the kick is a single stellar evolution process.
So you have a kick also in the first supernova?
Yeah.
Or you have it only for the second?
No, we have, for example, here I show you all the supernova kick that are bound. Sorry, all the neutron stars that are still bound.
But I mean the evolution of the binary.
Yes.
First you have one supernova that produces the neutron star from the primary, and then you have another supernova.
Exactly. Yeah.
So you have one kick at the beginning, and then you can disrupt the system, and then you have another one. Okay.
In a work I have done, I noticed that the first one is the critical kick, because at the beginning the star is usually wider.
Okay.
Instead, the second kick can be also strong, because usually during the evolution the system has been shrink. So a strong kick can also enhance the merger, because you obtain a higher centricity that make easier the merger. So you can merge in less time the black hole binaries of neutron star.
So it depends, because when you have the kick, you not only increase the eccentricity, but also you increase the separation. And the time scale for merging goes to the power separation and
True.
So in fact,
it's a complicated.
In the numbers, it's not so straightforward that when you have elongated orbit, you really merge fast.
True.
So, observation, how do you measure?
Sorry?
From the observational point of view, how you can measure the kick?
They do it from the parallax. So they take, for example, in OPS, the data from the proper motion of young pulsar, and they estimate which is the 3D velocity of the neutron star.
And so then how can you measure so small things then?
Here? For example, if you know also the velocity of binaries, for pulsar in binaries, you can, I'm not an expert in how you can compute the velocity, but if the velocity of a double pulsar, you have the velocity of the double pulsar, so you know how, what should be the maximum strength of the kick in order to not disrupt the binary.
So the Hopps curve is an arrow. Which how big is the error?
I don't know, I have to be honest, but yeah, I can show you from the paper. It's still uncertain because can be also an effect. I repeat, Hopps considers almost only single pulsar. So yeah.
The curiosity you cannot answer. It is not out of the exam. Because I saw you have a paper submitted in 2018, next slide or something like that, and we are at the end of 2019.
No.
So
yeah, sorry, it's a typo.
Okay, fine. Good for you.
Yeah. One last question, just to see if I understood correctly. So the effect of metallicity is that the metallicity decides the mass loss, basically through wind. That's the only effect that metallicity has.
I think it's the strongest one. But of course, because you change the mass during the evolution, also other parameters like the radii or the luminosity change. So the evolution along the HR diagram, it's different.
Yeah, but the main effect is on the mass loss.
I found that the mass loss is crucial.
In your initial distribution of mass ratios and separations, have you included results from the tarantula survey? Because that's, I think, the most prominent.
The SANA distribution, the distribution proposed by SANA, for the orbital elements. For the mass, I draw the primary from a cubo, and the secondary from the same distribution proposed by SANA for the ratio.
For the mass ratio,
So which was the distribution of separation, the 1/A or?
The separation, no, because SANA don't have the distribution for the separation, but for the orbital period.
Okay.
So it's also
you drive it up.
Yeah. I don't remember exactly which is the deviation.
Okay, so we will back.
Okay, thank you.
Ti lascio la cartellina.
Grazie.
Good. So, congratulations. You passed a very good thesis. Thank you very much. Okay, all in So, the next talk is now concerned something completely different. Yeah. And now for something completely different, multi-pilot, exoplanets and instruments, right? Yeah.
Yes.
Okay, and spaceborne satellites. Yeah. Okay, please go ahead.
Thank you very much. I started this PhD under the supervisor is Roberto Ragazzoni, Jacopo Finato, and the Professor Gianpaolo Piotto. Is now in Peru, right? He's me in this moment. I worked 3 years in the ASTRI integration and verification of 2 different projects. One is focused in a European Space Agency environment, is around the optical alignment and the qualification, test qualification of the telescope optical unit for PLATO. And the second one is the performance of the alignment procedure to the SHARK-NIR is a chronographic camera will be mounted in a large binocular telescope in Arizona. The main mission for the mission from PLATO is to reveal habitable planets around solar-like stars. I show you in this plot a selection of confirmed planets detected by transit radio velocity timing, mechanism, or astrometry. We compare with a selection with mass from 1 and 10 to 10 mass Earth masses and up to 2 radii of Earth. The stars with these planets are selected in mass around the mass of the Sun, and this creates in the zone, in the neighborhood of the zone, habitable zone where is the water is liquid in the surface of the planets. But we see that all confirmed planets is very close to the stars, and the zone of we have the planets is very without detection. This detection is made by tests and the Kepler tube and will be confirmed with characterization by Kepler. So it passes over Padova in 20 minutes. And PLATO will cover this gap. The scientific goal for PLATO is to measure with very high accuracy the radius of the planet by photometric transit, and with a campaign of ground-based follow-up in radio velocity, you can estimate with the same accuracy, 10%, the planet's mass to collect information around the density. But also with the astrocosmology on board of the telescope, we can define with accuracy also the stellar mass, the stellar age and the stellar radius to collect information around where is the habitable zone around this planet. The optical concept is ultra-high precision photometry, can reach 80 parts per million in photometric transit. The observation target is below 30 magnitude, for example, and with the concept is also long observation time. The payload concept is groups of 26 telescopes, with that grouped in 4 different groups. Each telescope is composed by the telescope of the units with I wanted to align. They merge the field of view, reach the huge field of 50 by 50 degree. But the most important thing is the cadence of observation. It's 25 seconds. Each 25 seconds we have an image for this field of view for all stars and 2.5 seconds for bright stars. PLATO is expected to launch in 2026 and position in Lagrangian 2 points. This is the expected, one of the expected sky coverage for PLATO. Is in black and dark blue. In dark blue there is the due north and south polar region with PLATO observed with a long duration, up to 2 years. And we have also 10 step and step field where PLATO we can observe from 2 months to maximum 3 months. I compare this sky coverage with the sky coverage from Kepler and the Kepler 2 mission. It's very large because PLATO is focused to detect solar stars nearby the sun. The optical design from PLATO is totally refractive. We use 6 lenses, all with a spherical surface, except the first lens we have a spherical surface, and the last one they are a flat surface for collect the focal plane array of the huge number of CCD. Important quality parameter is the square energy within 90% of the square energy within 2 by 2 pixels. The dimension of the pixel is 80 micrometers, and the working temperature is minus 80 Celsius degree. To align all these lenses, I need to select reference. I selected as reference the central lens, the lens made in calcium fluoride, and this lens made the reference for the position for all other lenses. The alignment requirement is to put inside the optical mounts the lens with accuracy in tip tilt less than 14 arcsecond, 22 micrometers in the center, and between 15 to 40 micrometers in Z position. But the optical alignment will be performed made in cold condition, 25 degrees, to achieve the best performance in minus 80 degrees. To do this, I use a ground super equipment. This instrument, these tools, where the optical mount is located inside this arm. L3 is inserted by the manipulator by the top in the middle. When the line L3 is in correct position, a laser fire a beam. This beam intercepts L3. L3 divided this beam in 2 parts. One part is back refracted to CCD2, can I use by tip tilt reference, and the other part pass through and is focused in the CCD4. This is the reference for the center for the lens. It is the reference for the tip tilt. The CCA, the ground super equipment, also allow the rotation of all mounts to allow the lens insertion order. This is, we start with L3, we rotate the mount, take another reference, we rotate again, insert L4 and rotate insert L2 and next to the last lens. The observer is this. I adjust the resume before. When the laser coming from the top, a part is transmitted and create an iris spot, Another part is reflected from the first surface and also from the second surface, and created in the back direction a shape. It's called Newton rings. This is the real image from all different ranks for Newton rings. It is achieved reference iris spot. We record that tip tilt is used by reference the Newton rings from L3, and at the center the iris spot from L3. But for the Z position, I use a coordinate measuring machine. With this machine, I touch physically the vertex of the lens to correlate this position with a 3D space with a reference to the optical bench. This is the optical bench when I finish the setup. This is the portion for the laser. There are here a setup with a coordinate cube to create a reference spot for the laser to perform stability over time, stability also over temperature. A 4D mirror creates the position of the laser inside the optical mounts, and this is the position from L3, the other lens. This is the manipulator, the control computers, and this is the coordinating machine. The accuracy for this machine is 20 micrometers. When I finish the alignment, this is the result for the accuracy. The tip tilt is achieved for all lenses are inside the tolerance design. But there are L2 and L3 slightly over the tolerance. I make more investigation about what is the problem, and the problem is borne by the ground support equipment, because the pivoting mechanism we need to improve by mechanical improvement. But there are many issues in the focus, because there is a very huge investigation, because this result coming from a very high error budget analysis. Each optical component was performed, for example, in stability and created this error. After this investigation, I found out there is problem is the touching machine, because for this machine we need a very high accuracy calibration, and also there is an intrinsic problem. The lens have a diameter from 120 meters, and we need to touch manually exactly the vertex. This creates an error. I investigated alternative methods to touch the lens without contact. For example, with the confocal sensing. The confocal sensing is not new techniques to locate the lens in the space by the optical beam, which is fused exactly in the edge of the surface for the lens. In this part, one part of the beam is back reflected. I can use this to locate the lens, change the focal length of the instrument. I can locate with what do you want accuracy. The minimum is 5 micrometers. I am happy because Leonardo, the former contractor for the manufacturing for this lens, used exactly these techniques to buy the first autocentric machine in Leonardo to make the alignment not only in Z position, but also in tip tilt and the center. If you are interested, I show you on the next. After the alignment, we perform optical quality test in Leonardo laboratory, putting the TOU inside a thermal vacuum chamber. This thermal vacuum chamber go down minus 80 Celsius degrees. But we wanted to perform the optical quality around all field of view of the TOU, and I use a 4D mirror that reflected the light from the collimated beam inside the thermal vacuum chamber. I performed 3 different tests. One is the ferrometric test, the anatomy test, and the PSF test. All these tests were compared with the ray tracing simulation to evaluate the optical aberration of the telescope, the n-square energy, the key parameter, and the focal image quality. Now I show you only the key test, the Hartmann test. The Hartmann test starts with a collimated beam and use an OLED mask. This OLED mask created many optical rays, and this rays is focused by the TU. With a CCD moving in intra and extra focal position with different steps, we collect many images. When I pass from intra and extra, all this spot are passing through the focus. To define what is exactly the position of the focus, I reconstruct by measuring and analyzing all images by the simple centroid, what is the path of all these rays, and what is the minimum area in the interception of this ray. This is for example, a simple focus analysis. This is the minimum size of this area, and in this position, this is the interception of all these rays. By this measure, I can evaluate the n-square energy. This is a very strong method because it's noise independent. And this is the results. I can explain you already this plot. We start with the cold condition. In solid black line, there is the nominal simulated performance for the TOU. The other black line is the best and the worst simulated case, applying the accuracy for the alignment. In a warm condition, the performance of the TOU is better than the best simulated performance. But there is a strange behavior when you pass to minus 80 degrees. Because this is, as the previous, the nominal and the worst simulated case, all measures are outside this limit. But if you pay attention, this feature is evident only with a large field of view. This is strange, and to explain what is the issue, we start with a very huge simulation in Monte Carlo, with use a more relaxed error for the coordinated machine from 20 micrometers to over 40 micrometers. This affected the Z position on 50 micrometers, and also we apply an error in manufacturing of the lens. For example, the thickness of the lens error is 20 micrometers and 0.4% in the region or curvature of the lens. What this manner appears with the nominal case, modified by these new errors, fit well the square energy. In conclusion, during my first 2 years of the PhD, I confirmed that the TOU have a procedure to be aligned and collect a very large number of lessons learned to improve the alignment in industrial contractor. And we perform quality testing warm and cold condition, and also explain what is the issue when it becomes from the field of view. Also, I delivered to the contractor this procedure, and all the work is collecting many documents, which is part of the preliminary design review we expect to finish in the early 2020. The next instrument is SHARK-NIR. SHARK-NIR is an instrument for direct imaging from exoplanet. For example, and the goal of this telescope is to detect young giant exoplanet around low mass stars. Because in this field, there are a new field of exoplanet research, because we don't know exactly how the solar system is born. And there is a beautiful opportunity in Tausia Auriga region, because there is a large star-forming molecular clouds where is located around 100 of these detectable planets, and also there are many moving groups with an age from between 10 and 10 to 100 mega years. But there is not the only science we can do with SHARK-NIR, because, for example, the field of the brown dwarfs, we can collect many data to explain if this object is formed by stars or is formed by planets, or also what is the interaction with stellar jet with the protoplanetary disk. But you can characterize also extragalactic objects like AGN or quasar. the science requirement design the scientific instrument. And SHARK-NIR is designed to reach 2.6 lambda/d in an inner Rocky angle, and I show you what is this name. And in contrast, we can reach 10 to minus 6 in contrast in a field of view of 18 by 18 arc-second. The position of SHARK-NIR in LBT, this is the LBT, is very near the instrument science location. Is here. The light passes through the large diameter in a secondary mirror and by the tertiary mirror in the focal position. And why exactly in LBT? Because LBT is provided with an extreme adaptive optics. We reach very high stellation, 90% in H band, and with high stellation, a coronagraph works very well. This is the principle with the coronagraphy works. We need to create a pupil plane, intermediate focal plane, and another one pupil plane. Because if I insert an aquadizer mask in the pupil plane, the waveform's intensity is changed in the focal plane. In the focal plane, for example, now see only the optical axis created by the stars in the middle of the field of view. The light from the star is located here, and the PSF is changed by the aquadizer mask. If I put inside here an occulter mask, the light from the stars is removed, but the light from a second source out of axis is not affected by this occulter mask. A secondary lens creates a secondary pupil plane, where is mounted a heliostope that removes the residual starlight. And at the finish, in the scientific plane, we have a discovery space with an inner, with large between the inner working angle and the outer working angle. In this region, the light from the star is totally removed in theory. This is the optical layout of SHARK to create all this plane. The light from the LBT coming from this direction and pass through the focal plane for LBT. LBT is a very crowded instrument and is composed by 3 flat mirrors, 1 deformable mirror, and 3 and 4 off-axis parabola. This is necessary to create the primary pupil plane. Is located in the surface of a deformable mirror. This deformable mirror works driven by a waveform sensor to remove the residual jitter inside the instrument. After this, we have the position of the apodizer mask, the position of the occulter mask near the secondary focal plane, and with the other mirror, we create the secondary pupil plane where is located the heliostope. The observing mode provided by all these instruments of these components are for classical imaging, coronagraphy, low resolution spectroscopy, and dual band imaging. The plate scale for SHARK is 1 milliarc arc-second per micrometers. This is the occulter mask when I use. And I characterize it, and I found a method to best align this inside the instrument. There are 2 different masks. This is the shaped cube mask located in a pupil plane with work with specific occulter masks to create around the PSF the discovery space. This discovery space has dimension from 100 to 300 milliarc, and the contrast start from 10 to minus 5 to reach 10 to minus 7 in theory, but in a small region. There is another one, coronagraphy filters, is the 4-quadrant phase mask. But this filter is not located in the pupil plane, it's located in the focal plane. In the focal plane you see the PSF of the star with the area rings because we have extreme adaptive optics. And the focal plane phase mask, the 4-quadrant phase mask, divided the stars in 4 quadrants, but only 2 of them are introduced with a shifting of pi. This shift creates a destructive interference in the secondary focal plane. and the light from the star disappears totally. The contrast will be achieved with this first mask is 10 to the minus 5, and we can reach more closer distance by the star with the object we want to investigate. I developed an optical bench to perform all procedure. This optical bench have 3 main parts. One is the source parts. We use a laser in 600 nanometer, another laser here is 300 nanometer. This creates the optical axis, which rotating in this manner. This optical axis passes through the pupil, a simulated pupil for SHARK, and very near there is the apodizer wheels. This lens, by this lens, created in an occulter field, occulter mask wheel, the exactly plate scale of SHARK. By a folder mirror here, we created the second pupil plane here, where is mounted the leostop, and finally the scientific camera is this. This CCD and this CCD created 2 reference images in transpupil to align all other masks. But there are also a secondary source, a line source with an narrowband filter. We created a secondary source exactly in the optical path, and I can move this secondary source around the space and also change this intensity. This is the simulator for a perfect planet. I write many code in Python. I create a library, and with this library I can align all masks in the center, keep tilt and focus. This is the results for the raw contrast for the shaped pupil. The shaped pupil will be mounted in a pupil plane. This is the symmetrical shaped pupil, an image in the optical bench. The PSF is changed to create the discovery space. When I introduce the occulter mask, I measure the raw contrast in the optical table. I reach the simulated performance. And with the asymmetrical pupil plane, the result is pretty the same. In the pupil plane, the shape is totally different. Also, the PSF changed, but in different manner. And the occulter mask create this dark zone, where I measure the contrast with fit well with the simulated case. But I can do another experiment to explain what is the performance. This is the profile for the from the focal plane, and I fine-tuning the intensity from a secondary source to the 8 rings. These 8 rings, by theory, is 10 to minus 4 the intensity with respect to the center. I move this source very near the inner working angle, and I show you what appears in the field of view of LBT. But this is not simulation, this is a real case. You see the star with high stereo ratio, but you don't see the planet. I insert the apodizer mask, and we created the discovery space, and at the end we insert also the coronographic, the occulter mask. This is the wheel with the return, and the starlight from the star is pretty totally disappeared, and this is the detected planet. I measured this with a filter with narrow band 40 nanometers, and the achieved signal to noise ratio is 40. 5 minutes, I finish. Is the last. This is the last the mask that we characterize. It's very difficult to characterize this mask because it's transparent, and this is the 4 quantum phase mask, and this is characterized by a discontinuity. To see this discontinuity, I use a fast rotating diffuser illuminated by green light, the laser from 500 nanometer. Why this laser? Because these 4 quadrants work in H band, and if you introduce a phase, it works with the wavelength. This is the plot for attenuation of this mask. This mask works very well in the H band, not invisible band. But there are a small windows Well, these filters work only also in visible part. I use 550 nanometer because this is my windows in optical alignment. But this is not is a new feature for alignment. This for quantum. I perform a Python code to detect exactly the center of this mask with a very high accuracy, 0.1 micrometers, and the PSF is fitted by a Gaussian fit. The major error is by the rotation of by piezoelectric motors. The final error budget is 5 micrometers, which means 6 milliarc second in the focal plane. If you remember, the minimum angle in inner working angle is 100. It's very, very high accuracy. This was appear when the center for the 4 quadral mask is exactly in the middle of the PSF, and in the puppy plane, normally the puppy plane is totally filled by the light from the star. The light from the star disappears literally totally, is put outside this puppy. Next, with the insertion from the helioscope remove also this, and we reach very high contrast in the focal plane. I try to estimate this performance by a contrast plot. This is the profile for the PSF before the insertion for the 4 quadrant and after. After we reach 10 to minus 4, if you remember the inner working angle from the shape pupil, 10 to minus 4 near, this is 1 lambda over d. The inner working angle for the shape pupils is 3 lambda over d, very close to the star. We compare these results also with the rejection factor in the 4 quadrant phase mask. Was born and designed in Paris at the Laser laboratory, and was tested in a working wavelength 1.6 micrometers with a resolution from the filter of 100. The rejection factor from the stars is 400, but the rejection is proportional to the square of the filter resolution. In laboratory in Padova, I used the totally different wavelength and a different resolution of the filter. And the expected rejection factor is 8. We reach 5 times more, 40 in rejection, because we have a very precise inaccuracy in position of the filter with respect to the PSF. In conclusion, I construct an alignment tool ready now for the integration phase with the mode is done in a clean room. I work in invisible light to best align an infrared instrument, and also we achieve the expected contrast in a shape pupil and also the expected rejection in a 4 quadrant phase mask. I start in last November the integration phase, and I hope that the commissioning phase in LBT start in July 2020. Thanks all, and very special thanks to my wife.
Okay, so you mentioned your wife. So the first question goes to your wife. Where is she? So what do you think about the work of your husband? Now this is a difficult topic for me, yeah. But one thing to clarify. I mean, this for SHARK, this looks like, say, you're preparing the instrument and you are in the commission, or you're expecting commissioning phase. But the example that you showed, you said it was a real one.
No, this is the real one. This is the real instrument.
But I think the instrument is still under construction and not yet on the.
Oh, okay.
So how can you observe with an instrument, a real object, if the instrument is not finished yet?
No,
this I don't understand.
No, okay. The fine tuning for the instrument will be computed in the commissioning time at the telescope.
Okay.
Now we need to perform all parts for the alignment for the instrument, because these tools, for example, for Python, will be used in July at the telescope.
Yeah, okay.
And if you use this shaped pupil, for example, we need to have an estimation, a real estimation, what is the performance. Also, in real condition, for example, in 1.6 micrometers. An example is, therefore, quantum phase match needed the PSF very in the center, very stable in the center for the 4 quantum. A part of SHARK-NIR I don't discuss here is the waveform sensor and the DM performance, and we close the loop to 1 kilohertz now in the laboratory with removing the residual jitter simulated in LBT. But this is very finished after the commissioning, because we have the telescope in my hand and we can tune the performance for the instrument.
Okay. Yeah.
Naive question about the alignment of the PLATO. Apart from the problem of the temperature, during the launch there are a lot of solutions. Is it possible to simulate and to predict
the prototype preliminary design review is a phase where the ESA want to collect many possible information around all parts of this project. I work in the optical line, but for example, another staff in the international group work in the vibration parts, another one in control in temperature, and another one, for example, in electronics. When I finish the optical alignment, the TOU start a cycle in temperature from 100 Celsius degree to down minus 18 Celsius degree, 10 times more times, okay? And at the finish of this cycle, we characterize the optical performance is very stable. Because I don't know if I say before, if 90% of a square energy is within 2 by 2 pixels, the photometric performance is 18 parts per million in the photometry in a 1 hour observation. If I change this performance, change the photometric performance. This is the problem. And there are another issue to solve.
You can check the performance after vibration.
In the space?
No, after the test.
Yeah, absolutely. There are many things. The prototyping phase is very important because when the constructor starts the manufacturing, there is not the time to solve the issue. We need now is the moment to solve the issue for the final integration.
A very nice question. Do you think that the performance of the colonographer depends on the seeing conditions?
Nice question. Nice question, because LBT is not in the space.
No, indeed.
Okay, there is here an image, I suppose. No, here. Yeah. If a LBT there is very bad seeing condition, the extreme adaptive optics works. It's normal. But with a 0 point in arc second, we can reach 10 to minus 6. Because at this level, the residual jitter is pretty totally removed. And for example, in the 4 quadrant, the star stay exactly in the middle.
So these conditions are met only
I don't know what is the probability of this situation. But the performance, for example, if your object is very near the inner rotating angle, this may be a problem.
And this contrast is maintained in an area. How large is the area? Sorry.
From 100 to 300 milliardsecond. Normally, if the object is far away from the star, you have more possibility to have a stability in contrast, because we are far away from the star.
This contrast is sufficient to get
okay, if
a planet like
if you are observing,
Jupiter.
yes, if you are observing a planet with 10 megayears in a star formation region in Taurus Riga is 140 per second far away from the sun. The mass, the limiting mass, the minimum mass is 4 Jupiter mass. 4 Jupiter mass. Because if the age for the planet go down, is very big. Yeah. For 100 mega years, the estimated mass is 5. And if deeper, you need more large planet normally. And the focus is we are very large region to investigate, because there are, for me, another feature in the coronagraphy. In the next future, we have large telescope, 30 meter, ELT, very large. This telescope needed to work with extreme active optic and extreme adaptive optics. With these new tools, the coronagraphy can open a windows in a discovery for exoplanet, because now we have 2 techniques, radial velocity and transit. In all of this method, we need a planet in a line of sight. But with coronagraphy, we discover all inclination. Very interesting.
Something I didn't understand. So for sharks, then, so there are different ways to mask the star. Is that correct? So the thing. So when do you use one technique and when do you use the
This
other?
depends from the source. For example, if you have a star with a jet, where is it? Here. If you have a star with a jet, you don't have interested to a large discovery space, because you have the jet, for example, in this part, not in the other part, and you can use a different apodizer mask to reach 10 to minus 7 in these small parts of the field. If you have a planet, for example, you need to have a very large field of view and you use a symmetrical one. If you have, for contrary, a double source very near, for example, IGN, you can use with high profit the 4 quadrant.
So how do you compare basically this with the VLT instruments, so sphere, for example?
Oh, so sphere is different, because sphere have different mode. In this part, the major improvement is the sphere is in the south part of the sky, and LBT is not part of the sky. And also, when PLATO, for example, started discovering new exoplanet, maybe also we found giant planet. And we need 2 instruments to make follow-up in a radial velocity, for example. In this case, we have a mode, low resolution mode, not for radial velocity, but to characterize the atmosphere of the giant planet, for example.
So, but it is better than sphere? It will work better than sphere, or the same performance as sphere?
I don't investigate the comparative performance. In this case, I remember where is the discovery space is pretty the same. The discovery space is pretty the same.
And the other
but there are another difference. LBT is one telescope with 8 meter size. This is 1 telescope. Yeah, I don't speak about. Is 1 telescope with 8 meter size, also for SHARK. But SHARK-NIR is the twins for SHARK-VIS, and in the same time, in the focal plane here, we are a large binocular telescope. If I don't use only this telescope for SHARK, in this moment in Rome there are the construction, the integration phase for SHARK-VIS, but we mounted in the same time in the secondary mirror focus for LBT, and we perform invisible part and the infrared part chronography. Well, of the same source. This is the improvement. Because we have two different fields of a wavelength we can investigate.
Yes, but very general and very basic. You talk about this new way of touching the lens. The question, did you already use it in Florence?
Yeah, no. I show you the...
And it is connected. Just a short answer. I mean, how much is standard and how much is innovative, the instrumentation that you have used here in the laboratory?
This is a very new instrumentation because the performance of space telescope and in astronomy we work with one telescope for community. Okay, but for example today starting Curie, the frigate and the Soyuz with sailing the telescope helps, but also Cosmos SkyMed. In the space telescope, the performance for Earth observation are very tight and very high huge of space telescope are put in the sky. The Leonardo work with one telescope for astronomy and, for example, from 10 to 100 telescope for Earth observation. And the performance achieved with the new techniques can allow Leonardo to reach best performance also with the other telescope. But this is interesting for Leonardo. Leonardo is a very old company in Italy that constructed the Asiago Galileo telescope, but in this example, use only centering machine without new methods. Trioptics creates 2 years ago one of these machines we locate the lens by a small beam of light without touching them. This is the machine with Leonardo by Trioptics and is now in integration in the laboratory. But this is the first time with an older company like Leonardo use one of these. And I am very happy because group of people on Leonardo come here to see PLATO and what is the step of the procedure, and I show you in my laboratory the test because I performed the test with not simulation with a real lens, and I demonstrate what is the accuracy of the methods. This great idea, and next start this new feature.
Okay. One last question, maybe. These stars for SHARK, M stars, these are they show variability. They have rotation. But is this a problem for the experiment? I mean, it changes the contrast certainly.
No, okay. If there is a bright spot, for example, or a high activity, the contrast is 10 to minus 5, for example, and the cost of the detection is become very high, more high, and your planet disappear during the flare.
Okay.
But for example, PLATO is calibrated to see G stars, not M stars. SHARK can investigate also many other.
Okay. Okay. So thank you again.
Thank you. teorini che possono dare il contributo per questo. Lo so che dicevi. L'aspetto dopo la gara gli marini. Prima avevo sentito adesso il tempo per
anche lei detto abbiamo contato
adesso
abbiamo deciso di regalare una
Martina, grazie per aver cancellato la diretta del dottorato. Se l'ho cancellato svuota il cestino. L'hai cancellato? Sì? Fortuna che non hai svuotato il cestino. Comunque svuotalo pure. Sì, è andato molto bene. Beh, quando è tutto qua? Ah, devono venire per la
vi faccio vedere io il ho già i dati, anzi io c'è
Okay, congratulations to your very good thesis, yeah? Very nice work.
Thank you,
yeah.
thank you very much. Grazie Mauro, grazie. Grazie Mauro, grazie.
Okay, thank you also to the audience.
della laurea,